Now that we have found the fixed points for a system, we may be interested in how the model behaves if the population is very close to this fixed point, but not equal to it. This can be done by linearly changing the population from the fixed point and seeing the resulting behavior, hence the name linear stability testing. To do this, we first introduce a new variable we'll call n hat, which represents a small change from the fixed point. We then add this small change onto n star and are able to see how this new population behaves in the model, with nt is equal to n star plus n hat t, which this implies that nt plus 1 equals n star plus n hat t plus 1. Now, when we substitute this into the governing equation of nt plus 1 is equal to nt times ft, which equals h of nt, it becomes n star plus nt plus 1 is equal to n star plus n hat t times some function n of n star plus n hat t, or h equals n star plus n hat t. Now, if we use this expression and take a Taylor expansion about the right hand side only around some point n hat t that is very small, we get n star plus n hat t plus 1 is equal to hn star plus h prime n star n hat t plus some higher other terms. Now, noting that n hat t is very small, to increase the power of n hat t, we'll make it even smaller to the point of being negligible for this approximation. Since h of n star is equal to n star, as given by the definition of a fixed point, this expansion simplifies down to n star plus n hat t plus 1 is equal to n star plus h prime n star n hat t plus 1. Oh no, n hat t even. And this is all equal to nt plus 1. Now this can further be simplified by removing the n stars, as they will just cancel out, to give n hat t plus 1 is equal to h prime n star n hat t. H prime n star will give a constant, so n hat t plus 1 becomes some scalar of n hat t. The value of this constant will dictate the behavior of n hat t plus 1. As we can see below, n hat 1 is equal to h prime n star times n hat 0. Running this simulation again, so the next n hat t plus 1, n hat 2 is equal to h prime n star times by n hat 1. And we can then use the previous result to substitute in for n hat 1, and this gives us is equal to h prime n star times h prime n star times n hat 0, or h prime n star squared times n hat 0. Running it a third time will give us n hat 3 is equal to h prime n star to the 3, or cubed, times n hat 0. Now, in general terms, as this increases up to t, it becomes n hat t plus 1 is equal to h prime nt times n hat t, and we know that n hat t is just h prime n star to the power of t times n hat 0. Now this allows us to see how the small change will behave in the model as time goes on. Based on the different values of h prime n star, we can now formulate a definition for the stability of a fixed point. If the modulus of h prime n star is greater than 1, then as time increases, h prime n star to the t will increase away from 0, so the value of nt plus 1 will increase as well. This is known as an unstable fixed point. If h prime n star is less than 1, then as t increases, h prime n star to the power of t will decrease towards 0 because we're just timesing it by a smaller number each time. So the value of nt plus 1 will tend back to the fixed point n star. This is known as a stable fixed point. Now there are two types of stability and instability that we will look at. These are monotonic and oscillatory. Monotonic stability occurs when h prime n star is less than 1. This satisfies our definition for stability, and it means that given a small change to a fixed point, the population will return to the fixed point from the same direction, as you can see in the diagram. Monotonic instability occurs when h prime n star is greater than 1. This satisfies our definition for instability, and it means that given a small change to the fixed point, the population will tend away from the fixed point in a single direction or in a monotonic way. Oscillatory stability occurs when h prime n star is between -1 and 0. This satisfies our definition due to the modulus function, meaning it becomes a positive, and means that this will, given a small change to a fixed point, the population will tend to the fixed point from both sides, so it will alternate which side and slowly come in closer. This is due to the negative nature of h prime n star, as when you raise this to even powers, it will give you a positive, and odd powers will give you a negative scale to the perturbation. Oscillatory instability occurs when h prime n star is less than -1. This again satisfies our definition due to the modulus function, and means that given a small change to the fixed point, the population will tend away from the fixed point in an oscillatory manner. Again, because it's a minus, when you raise it to even powers, it becomes positive, odd powers becomes negative. It's important to note here, when h prime n star is equal to -1, the point just becomes oscillatory, and it will simply change from n plus n hat t, or n star plus n hat t, to n star minus n hat t for all t.